Equiangular Triangles, and Thales Observation. Welcome back, everyone. Before we dive into today's new material, let's take a moment to reflect on what we've already covered. In our previous subsection, we explored the general conditions required for polygons to be considered similar. Now, keep in mind that a triangle is simply a specific type of polygon, one with exactly 3 sides, so all those fundamental rules we discussed previously apply directly to triangles as well. Today, however, we are going to narrow our focus. We will be looking at a very specific type of similarity called equiangularity, and we'll explore a fascinating mathematical observation made by the ancient Greek mathematician Thales, which links these angles to the lengths of the sides. Understanding equiangular triangles. Now that we've established that the rules for polygon similarity apply to triangles, let's dive into what makes a triangle equiangular. When we use the term equiangular, we are focusing specifically on the angles of the triangles rather than their side lengths. By definition, 2 triangles are considered equiangular if their corresponding angles are exactly equal. To make this concept concrete, let's look at 2 triangles, delta ABC and delta PQR. For these 2 triangles to be equiangular, we need to see a perfect match in their angles. Specifically, angle A must equal angle P, angle B must equal angle Q, and angle C must equal angle R. Now, here is a crucial point to keep in mind before we move on to Thales' observation. Being equiangular does not necessarily mean the triangles are the same size. One could be much larger than the other. What it does guarantee is that they share the exact same shape. Thales' observation. This brings us to Thales' observation. Thales was an ancient Greek mathematician who noticed a fundamental relationship between the angles of a triangle and the lengths of its sides. He discovered that when 2 triangles are equiangular, they aren't just similar in shape. Their sides actually follow a very specific pattern. Here is the core principle you need to remember. In any 2 equiangular triangles, the ratio of any 2 corresponding sides is always the same. To put this into mathematical terms, let's look at our 2 triangles again, delta ABC and delta PQR. If these triangles are equiangular, then the ratio of side AB to side PQ is equal to the ratio of side BC to side QR, which is also equal to the ratio of side AC to side PR. What does this actually mean in practice? It means that the scale of the triangles is consistent across the entire shape. For example, if you find that one side of the second triangle is exactly double the length of the corresponding side of the first triangle, you don't need to measure the others to know they are also doubled. Every single side of the second triangle will be exactly twice the length of its corresponding side in the first triangle. Now that we have established what it means for 2 triangles to be equiangular, meaning they share the exact same angles, let's look at a groundbreaking discovery that connects those angles to the actual lengths of the sides. This concept of a constant ratio is exactly what we are going to apply in our next slide, where we'll see how architects use this very principle to create accurate blueprints. Real-world example, architectural blueprints. Imagine you are looking at an architect's work. Suppose an architect is designing a triangular support beam for a roof. To plan this, the architect first creates a small-scale drawing, which we call a blueprint, and later, the construction team uses that plan to build the actual, full-sized beam. Let's look at a specific scenario. Suppose our blueprint triangle, which we will call triangle A, B, C, has angles of 90 degrees, 60 degrees, and 30 degrees. Now, the actual beam, which we will call triangle P, Q, R, is built using those exact same angles, 90 degrees, 60 degrees, and 30 degrees. To solve problems like this, we can follow a simple 4-step analysis. Step 1 is to identify equiangularity. Because both the blueprint triangle and the actual beam share the exact same corresponding angles, we can formally state that triangle A, B, C, and triangle P, Q, R are equiangular. Step 2 is to apply Thales' observation, which we discussed in the previous slide. Since we have confirmed these triangles are equiangular, we know that the ratio of their sides must be constant. Step 3 is to calculate the scale factor. Let's say the side A, B on our blueprint is 10 centimeters, and the corresponding side P, Q on the actual beam is 200 centimeters. To find the ratio, we divide A, B by P, Q, which gives us 10 over 200. When we simplify that fraction, we get a ratio of 1 over 20. This tells us the actual beam is 20 times larger than the blueprint. Finally, in step 4, we can use this ratio to determine other unknown sides. If we know that side B, C on the blueprint is 15 centimeters, we can set up our proportion. 15 divided by Q, R equals 1 over 20. By multiplying 15 by 20, we find that the actual beam side, Q, R, must be 300 centimeters. Now that we have established the theoretical definition of equiangular triangles and Thales' principle of proportionality, let's see how this actually works in a real-world application. As we move to the next slide, keep this calculation in mind, because it is very easy to make mistakes when pairing these sides incorrectly. Common mistakes to avoid. First, please be careful not to confuse equiangular with congruent. This is a frequent error. It is tempting to assume that if two triangles have the same angles, they must also be the same size. However, as we discussed in our earlier slides, that is not necessarily true. While congruent triangles are identical in both their angles and their side lengths, meaning they are exact carbon copies, equiangular triangles only guarantee that the shape is the same. They can be vastly different in size, much like the small blueprint and the large construction beam we looked at in our architectural example. Second, watch out for the incorrect pairing of sides when you are calculating ratios. When you are setting up your proportions, you cannot just pick any two sides at random. You must ensure you are comparing sides that are corresponding. A great way to do this is to look at the angles. Always ensure you are comparing sides that are opposite to the equal angles. For instance, if angle A is equal to angle P, then the side opposite to angle A, which is side BC, must be compared to the side opposite to angle P, which is side QR. If you pair them correctly based on their opposite angles, your calculations will remain accurate. Now, before we wrap up today's lesson, I want to pause and address two very common pitfalls that students often encounter when working with these concepts. It is crucial to master these distinctions to avoid losing marks on your exams. Keep these 2 points in mind as we move into our final summary. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session to ensure everything is clear. First, let's revisit the definition of equiangular triangles. Remember, as we discussed in our second slide, these are simply triangles where the corresponding angles are exactly equal. It is all about the angles being identical. Next, we have Thales' observation. This was the core principle we explored earlier. Thales discovered that if you have two triangles that are equiangular, their corresponding sides aren't just random, they are proportional. This means they change at the exact same rate. To put this into a mathematical formula, as we saw in our step-by-step analysis, if we have triangle ABC and triangle PQR, the relationship is expressed as the ratio of side AB to side PQ is equal to the ratio of side BC to side QR, which is also equal to the ratio of side AC to side PR. This constant ratio is what maintains the similarity between the two shapes. Finally, I want to emphasize one last time the distinction between shape and size. As we cautioned in our common mistakes slide, equiangularity guarantees that the two triangles have the exact same shape, but it does not mean they are the same size. One could be a tiny blueprint and the other a massive structure, but as long as the angles match, the shape remains preserved. Please review these points carefully, and if you have any questions regarding these proportions, feel free to ask.